Algebra students, lesson 19. There's only 20 lessons in the unit. This is lesson 19, and it's going to be a bit long. So what I would recommend is you watch it. At the end, I'll try to tell you about how long it is. You watch it for maybe 15 to 20 minutes. Take a break, get a snack, stretch, do something else, and then finish. Okay? It's a long one, but we're going to do it in one day because the homework is fine. All right, let's do it. First of all, this right here, I don't believe it's in your notes. Let me look really quick. Sorry, hold on. It's not, but I put it in the lesson because it is called the correlation coefficient. It's what your coefficient. It's what your calculator spits out when you do linear regressions. So it's super duper important. And because this equation looks, yikes, hard, we love that our calculator spits it out for us. The correlation coefficient is R. Not R squared, just R. So let's dive in. So positive and negative linear relationships. Linear relationships can be described as either positive or negative. Below are two scatter plots that display a linear relationship between two numerical variables, x and y. All right, the first question, which I actually have in the next slide, but I need this to look at to answer it, asks, the relationship displayed in scatter plot 1 is a positive linear relationship. That means as this increases, that increases. So as our x's go up, our y's go up. And we can sort of see that pattern there. Does the value of the y variable tend to increase or decrease as the value of x increases? If you were to describe this relationship using a line, would the line have a positive or negative slope? It is an increase, therefore a positive slope. The relationship displayed in scatter plot 2 is a negative linear relationship. That means as x increases, y decreases. It sort of goes like that. As the value of one of the variables increases, what happens to the value of the other variable? If you were to describe this relationship using a line, would the line have a positive or negative slope? So the other variable actually decreases, which gives us a negative slope. Check, check. What does it mean to say that there is a positive linear relationship between two variables? When you have a positive linear relationship between two variables, that just means as one variable increases, the other variable increases. What does it mean to say that there is a negative linear relationship between two variables? Well, it's just the opposite. As one variable decreases, the other variable also decreases. All right, moving on to example 2. There are 5 examples just to prepare you. Below are two scatter plots that show a linear relationship between two numerical variables x and y. Okay, if I look at question number 5, it says, is the linear relationship in scatter plot 3 positive or negative? This one's not quite as clear cut, but it looks as though as the x increases, the y's increase, but those decreased. It's just not quite as clear. So number 5, my answer would be not as clear. It's not very apparent. We think it could be positive. It looks like it may be positive. How about 4? As x goes, what does y do? I mean, that one looks like it could be positive too. So that's also not as clear. It could be positive. Check, check. It is also common to describe the strength of a linear relationship. We would say that the linear relationship in scatterplot 3 is weaker than the linear relationship in scatterplot 4. Why do you think a linear relationship in scatterplot 3 is considered weaker than the linear relationship in scatterplot 4? That's one for opinions. 3 looks a bit more scattered if you look at it. If I can spell, love spelling. It's very important in life. I do my best and I try really hard. So I would say 3 is more scattered. You could also say they do not cluster tightly around a line. And if I look at number 4, I'll write down here, if I look at scatter plot 4, the points confirm a lot closer to a line. If I look at question number 8, what do you think a scatter plot with the strongest possible linear relationship might look like if it's a positive relationship? Draw a scatter plot with 5 points to illustrate this. Well, if it's a really strong linear relationship and you've got 5 points, let's put them on the points. I made that a slope of 1. If you look, up 2 over 2, up 2 over 2, up 2 over 2, up 2 over 2, up 2 over 2. My slope is somewhat perfect. But here, you need your points have to be in a straight line. Okay. Yeah, what else could I tell you about this? My points form a straight line. It has a positive slope. Looks pretty good. How would a scatter plot look? How would a scatter plot that shows the strongest possible linear relationship that is negative look different from the scatter plot that's positive? Well, I would start up here. Sort of trying to do the same type of slope. Yep, looks good to me. You need a line. So pretty straight with a negative slope. Consider the 3 scatter plots below. Place them in the order from the ones that show the strongest linear relationship to one that is the weakest linear relationship. That's an awesome one. I really like it. Let's see. This one, I'd say looks awful. It's like that, right? This one, but still, it's a better line. So that's pretty good, and that's pretty stinky. Explain your reasoning. Well, it's what I said out loud. The last one was scatter plot 7. We had a really straight line. Can't spell. There we go. We had a really straight line. It looked really good. And then scatter plot 6, you had, let's see, really just like 1 point out of place. And then scatter plot 5 was crazy. It was almost like, shotgun. That's the word I was looking for. It took me that long to figure out that word. But it was crazy. It looked like a shotgun blast. Had almost no rhyme or reason to it. Number 12. Which of the following scatter plots shows a stronger linear relationship? Think carefully about this one. I don't know, if I drew a line here, that looks like a crazy one. If I drew a line here, that one looks like a crazy one. I don't know. It looks pretty similar to me. But one, let's see, I can't say one. Number 8 is negative. And number 9 is positive. Yep, that's really it. Cool. Example 3. Like I said, there's 5 examples, but we're doing great on time. The correlation coefficient, the point of the lesson, is the number between -1 and 1, including -1 and 1, that measures the strength and direction of a linear relationship. The correlation coefficient is denoted by the letter R. Several scatter plots are shown below. The value of the correlation coefficient for the data displayed in each plot is also given. Beautiful line. Perfect correlation coefficient. Okay. Interesting line. Sort of made it in the middle. Not as good, not as close to 1. Okay. Here we're getting a little crazy. I'm not even sure how to draw it. Further away from 1. Okay, I don't even know what to do with this one either. It looks like it might be slightly negative. Okay, a little bit better. Still not good though. A little bit better, still not good, and perfection. When is the value of the correlation coefficient positive? When the relationship is positive. When the slope is positive. When is the value of the correlation coefficient negative? When the relationship is negative. When the slope is negative. Is the linear relationship stronger when the correlation coefficient is closer to 0 or closer to 1 or -1? Okay, that's the best, when it's closer to 1 or -1. So looking at the scatter plots in example 4, you should have discovered the following properties of the correlation coefficient. Property 1, the sign of the correlation coefficient corresponds to the direction of the linear relationship. Positive relationship, negative relationship, positive slope, negative slope. Property 2, R equals +1, perfect positive relationship. All points in the scatter plot falling exactly on a straight line. Property 3, -1 is a perfect negative linear relationship. And then property 4, the closer the value of R is to positive or -1, the stronger the linear relationship. Steps for calculating. We've actually already done this. So let's read through it. Determine which variable represents X and Y. Put it into list 1 and list 2. X in list 1, Y in list 2. Select stat. Let's see, we want to do calc, linear regression, L1, L2, enter. The value of R, which is the correlation coefficient, should appear on the screen as long as you have your diagnostic on, which you find by going through the catalog. So turn your diagnostic on and hit enter, and you find that through the catalog. So here we're going to practice calculating our coefficient. We've used this one before, right? Shoe length and height. Plug that into list 1 and list 2. So yes, go ahead and enter the shoe length in your calculator for list 1 and list 2. Do the linear regression, and then find the correlation coefficient. I went ahead and did that, and I got a correlation coefficient of approximately 0.6. Okay, here we have a great table of if the correlation coefficient is there, what is it good data or not. 0.6 falls in right there, so there's moderate positive linear relationship for 0.6, which is a question right here. Interpret the value of the correlation coefficient between the shoe length and the data. That was the moderate positive relationship. All right, here we have fast food items. The table displays the fat content and the number of calories. Go ahead and put that in your calculator under list 1 and list 2 and practice. We've got our scatter plot right there. It looks to be a positive relationship. But go ahead and do your linear regression and look for your correlation coefficient. So based on the scatter plot, do you think the value of the correlation coefficient between fat content and calories will be positive or negative? We just said, I believe it's going to be positive, because as x increases, y also increases. It looks like it has a linear relationship, positive. Based on the scatter plot, estimate the value of the correlation coefficient between fat content and calories. Ooh, I'm going to guess at 0.75. I don't like guessing. Calculate the value of the correlation coefficient. So that's by calculating your linear regression, like I said earlier, which I'm going to go ahead and do. Give me a second. Oh, I failed miserably. I should have looked ahead. 0.44, which again is moderate. If you look at that chart, a moderate linear relationship. Can you even read that? Cool. All right, one more. We have this data. L1, L2. We're still positive linear relationship. I have no idea how strong the correlation is, though. Yeah, I really don't enjoy that. Let's see what happens. Based on the scatter plot, do you think the value of the correlation coefficient between sodium content and calories per serving will be positive? Because as x increases, y increases. I think it's a positive linear relationship. Estimate the value of the correlation coefficient. I have not cheated, but I'm still going to guess about 0.75 because I think it looks pretty good. But now let's go ahead and use our calculator to figure out the correlation coefficient. So calculate the value of the correlation coefficient between sodium content and calories, round to the nearest hundredth. Went ahead and calculated it. I got 0.79. That's just luck. I guessed. I thought it was a great relationship, but I thought the last one was too. That indicates a strong positive relationship from that table a few slides earlier. So when we did fat content and number of calories. What did we get? I think it was 0.4. Yep, 0.44. And then sodium content was 0.79. So that one right there is stronger. It does surprise me. You would think fat content and number of calories would be the stronger linear relationship than sodium content and number of calories. Crazy. All right, the last slide, example 5. Correlation does not mean that there is a cause and effect relationship between variables. It is sometimes tempting to conclude that if there is a strong linear relationship between two variables, that one variable is causing the value of the other variable to increase or decrease. But you should avoid making this mistake. When there is a strong linear relationship, it means the two variables tend to vary together in a predictable way, which might be due to something other than a cause and effect relationship. For example, the value of the correlation coefficient between sodium content and number of calories for fast food in the previous example was R equals 0.79, indicating a strong positive relationship. This means that the items with a higher sodium content tend to have a higher number of calories. But the high number of calories is not caused by the high sodium content. In fact, sodium does not have any calories. What may be happening is that the food items with high sodium content also may be the items that are high in sugar or fat. And this is the reason for the higher number of calories in these items. Similarly, there is a strong positive correlation between shoe size and reading ability in children, but it would be silly to think that having big feet causes children to read better. It just means that the two variables vary together in a predictable way. Can you think of a reason that might explain why children with larger feet also tend to score higher on reading tests? Larger feet may be that they are older, therefore can read better. That's my guess. All right, good job today. It ended up being not as long as I thought it would be. So good work.